Okay, so we are doing question one, part B. So this is on ET42, 23rd of June 2012, Electrician's Theory exam. So, Class 1 plug-in heater is designed for use on a 230-240 AC supply. An ohmmeter gives a reading of 24 ohms measured at a plug. Use calculations to show the supply voltage being used if the power dissipated is 2,204 watts. Now, you can try and remember the formulas, or you can actually use your aspect formula sheet for this one, and we're after this wheel. So we're getting the voltage, and we've got a known power and a known resistance. Right? So in this case, our formula V equals the square root of P times R. Right? So V equals, and so we were given a power of square root of 2204 times by our 24. V equals, and we grab our calculator, 2204 times by 24 equals, and then square root of answer equals 229.991. Rounding to two decimal places, so one doesn't round up, it's 229.99 volts. So we actually look at their answer, they put in 230. Taking pick on what you prefer to do. Most of the stuff nowadays asks for two decimal places. Moving on to the next question, question 2. Skipping the others because they're not maths based at this stage. I'll do a full exam walkthrough later. So, question 2. A three-phase star-connected commercial oven draws 32 amps from a 400-volt supply and is protected by a 40 amp GG-HRC fuse with a utilization category or fusing factor of 1.5. Use the information in the introduction to answer parts A and B. So, first, let's draw the oven. Before I even read any further, we have star-connected oven. So we've got an element there, element there, element there. Then our oven comes out to our three phases. And we know it's got a 40 amp fuse times 3. And we know it's drawing 32 amps. 400-volt supply, so that means our voltage here is actually going to be 230.94, and our voltage here is 400 volts. Always good to draw a drawing for these questions, otherwise you get lost in the words. So, an earth fault loop impedance test for the oven shows a reading of 0.38 ohms. While the oven was operating, a fault of 5.6 ohms has developed between the blue phase and the oven frame. So we're dealing with the oven frame. And this will be earth. And we know that we've got a 0.38 earth loop impedance. So that's going to, it's not just the earth wire, it's actually also combined with the phase. That's coming from the star transformer that's feeding it. So that comes off there, and then say that one comes off there, for example, and then these two can be the other two. So they want calculate the total current flowing in the faulty blue phase. So we're going to have 32 amps plus we're going to have 230 volts, 230.94 volts going that way. And it's on a fault of 5.6 ohms. So we haven't been told that this element's burnt out. So we're going to have 32 amps to the element, but the fault itself is going to be 5.6 plus our 0.32. So R equals 5.6 volt plus 0.38 earth loop impedance. So our current amps equals volts divided by resistance. Amps equals 230.94 over, and our resistance will be 5.6 plus 0.38. Put that in brackets. Amps equals, I always like to do the brackets first manually, so 5.6 times 5.38. And then we get to our 230.94 divided by answer, and we get 108.52. Two thirty point nine four. Thinking something that's wrong. Must have had a typo. 38.62 amps. I wrote it 5.6 plus 0.38, and then 230.9. Sometimes you will hit the wrong key and you won't notice. So calculate the total current flowing in the faulty blue phase. It'll be that plus our 32 amps, because they asked for flowing in the faulty blue phase, not flowing in the fault. So 8 plus 2, 10, so 3, 6, 7, 70.62 amps. Final answer. Heard that. Yeah, so I don't misread stuff. So they've got 230 instead of 230.94, which is how we end up slightly different. Still got the 5.6 plus the 0.38, and then that ends up with a 38.59, giving us a total of 70.59 amps. So the 40 amp fuses have a fusing factor of GG utilizing. That one I have to explain using calculations the effect on the operation of the fuse. So the fusing current is 1.5 times, as they stated earlier on. So 1.5 times 40 gives you 60 amps. The fuse will operate as the fault current of 70.59 amps is more than the fusing current of 60 amps. So it is going to melt. It's just a question of how quick, because this is an overload, not a short circuit. A short circuit on a GG fuse is typically 7.5 times its rated current, so 40 times 7.5 would be 300 amps. So we're not expecting an instant loss of power, or less than 0.4 of a second, which is the legal minimum. What we are actually expecting is a slow fizzle that could take an hour or two. So not an instant disconnection of supply. On another occasion, the earth fault and leak impedance for the oven was 4.84. So 4.8. Due to a high resistance joint, while the oven was operating for 5.6 ohms as developed, so it's still the same fault, between white phase and the oven frame. Calculate the total current flowing in the faulty white phase. So we're doing exactly the same equation. The only difference is instead of 0.38, we're using 4.84. So 5.6 plus 4.84 gives us 10.44. Just since they're using 230, we'll use 230 volts. So 230 divided by answer, and we get 22.03. So we're now going to have a fault current of 22.03 amps plus our 32 amps from the oven. So we're going to end up with 454.03 amps total. We look at the answer sheet, they have the same thing, 54.03. Now, explain using calculations the electrical hazard to the user of the oven. So we have flowing through this wire here our 22.03 amps. So that's flowing down this wire back to our earth or any endpoint. The calculation we want to do is volts equals amps times resistance. So volts equals, and this is once again from our little nice wheel here. Volts equals amps times resistance. We've already got the amps in the calculator, so times by our resistance, which is 4.8, and we end up with 105.747, so 75 volts. This is enough voltage for you to feel. So that's the thing we're next doing in question B2. It's explain using calculations the electrical hazard to the user of the oven. The electrical hazard is it's not going to trip because you've got 105.37 volts for the person to feel, and the actual current flowing, because we've got 22 plus 32 is 54 amps, and these require 60 amps to even start melting. That's never going to disconnect the supply. And now we're on to question 3. Was it from Okay, so we are working on Et42, Electrician's Theory Exam, 23rd of June 2012. So to start with, introduction, we have a 250 kVA 3-phase delta star connected step-down transformer, has a phase turns ratio of 287 to 1. The primary is connected to a 66 kV 3-phase supply. The transformer is fully loaded. Okay, calculate the secondary phase voltage. Whenever you're dealing with transformer questions, the first thing you should do is draw the problem. Don't start doing maths to start with. So we have it is a 250 kVA, and then we have its delta star. So we have our delta, we have our star, and it's a step-down transformer. So left-hand side is the primary, 287 to 1. Primary is connected to 66 kV. So 66 kV. 3-phase supply, fully loaded. Calculate the secondary phase voltage. So all we have to do is go 66 divided by 66 divided by 287, and then times by 1000, it was kV, and we get 229.96, so 965, so 97 volts. And if we look at our answer sheet, they gave us 230 volts. So they didn't do to 2 decimal place, but same deal, same calculation. Then we move on to the secondary line voltage. So line voltage is between there and there. It was phases that we were comparing for. So we times that by the square root of 3, and we get our 398.311, so 31 volts. They had 398.36 because they rounded. Same answer, there's a level of fudge when you're doing these exams. Next, we'll calculate the primary line current. So for that one, we use our 3-phase formula. So 3-phase power formula is P equals square root of 3 times V line times I line. Now, or KVA or VA, or P kind of interchangeable. The difference is whether or not we've got power factor. So in this case, our VA is 250,000 equals root 3 times 66,000 times I line. So we want to make that so it's just I line equals. So we divide by the square root of 3 times 66,000. Oops. And then this one here, because we have to do the same on both sides, square root of 3 times 66,000. And then the square root of 3's cancel, the 66,000's cancel, so we're left with just I line. So now we can write I line equals, and we go 66,000 times by square root of 3, and then 250,000 divided by answer, and we get 2.186, so 2.19 amps. And if we look at our answer sheet, it says 2.19 amps. Now calculate the secondary line current. So the formula doesn't actually change. However, our line voltage changes. So instead of 66,000, we're using 398.31. So that's still square root of 3 times, and that's still 250. And so our I line equals, so 398.31 times square root equals, and then our 250,000 divided by answer gives us 362.374, so 37 amps. We look at our answer sheet once again, they had 362.34. That's a rounding error difference. Once again, it will be ignored. Now, our next couple of questions I may as well go through while I'm here. State one reason why a current transformer is dangerous when its secondary line is left in the open circuit condition. So current transformers are designed to be permanently short-circuited, and then you measure the current flowing through. If you don't short-circuit them, they generate very high voltages across their terminals, and that can damage the current transformer with insulation breakdown, as that voltage is allowed to climb that high, because you actually have a pretty close 1-to-1 ratio type of thing going on sometimes, or it's arguably a step up transformer, so you're stepping up the 66,000 kV into the high voltage. And then stage one, practical method used to reduce the iron loss of a transformer when it is constructed. And so this is where we laminate the iron cores so that we don't have the eddy current going through them. And we also use special types of steel, such as silicon steel, which has a very high internal resistance, once again reducing those eddy currents. And that is the end of question 9.